Henning Syversen, Chief Executive Officer of Triton Hydrogen, leads innovation from Norway, spreading it worldwide. A notable achievement is the development of the world's first nano-coating with a 100% barrier against hydrogen permeation, showing Triton Norway's commitment to sustainable advancements and hydrogen future. This is the Energy News Biz interview series. To support it, please check out our advertising options in the description. Thank you. And now, here's Henning Syversen. Who is Henning Syversen?
Yeah, hello. My name is Henning Syversen. I am the CEO of Triton Hydrogen. It is a UK-registered hydrogen technology company based from the Triton Norway group of companies doing green technologies.
Can you elaborate on the current state of hydrogen leakage detection technologies and their scalability for different applications?
The hydrogen permeation and leakage issue have been as old as hydrogen gas itself. So for about 100 years, there have been attempts to try to isolate hydrogen completely and stop the hydrogen permeation. There has been different kinds of approaches. Some are material-wise, using novel materials trying to stop the hydrogen. We have a different approach. We have gone for a coating. It's a nano-based coating that has proven to completely 100% stop the hydrogen permeation, and also then the steel embrittlement. And also in other materials, it has stopped microcracking in plastics and so on. So there's been a lot of different approaches to that. The good thing about coating is that you can retrofit existing pipe infrastructure, etc. And it's a lot cheaper to both produce and to implement. So that's why we have chosen to go for this route. It's been a 5-year journey for us to tweak our nanotechnology into a hydrogen barrier. As I said, it has been tried for 100 years, and it took us 5 years to do it. Globally, there has been spent billions of dollars trying to find a hydrogen barrier through different like universities and R&D facilities, the industry itself, etc. So to a certain degree, some coatings have managed to do 90+ percentage of delaying the actual permeation. But as far as we know, our Triton X hydrogen barrier coating is the only one in the world who have passed the ISO 17081 hydrogen permeation standard with an absolute 000 permeation of the hydrogen. So that in that sense, it's a game changer, because now you can long-term store hydrogen for years, which has up till now been impossible.
I will certainly go back to that. Now, in terms of regulations, how do you envision the coordination process at the national and international levels to achieve coherent regulations?
Well, today, hydrogen is based on the hydrogen regulations, and like natural gas has another regulation. And our hope is that, of course, proving that the hydrogen is absolutely isolated from the storage material, being whatever, steel or plastic or carbon fiber or whatever it is, the industry can change the regulations from hydrogen regulations to the easier natural gas regulations. But we're working politically and environmentally, looking at these things to make it easier for the industry to handle hydrogen, which we are sure we can accommodate by making sure the hydrogen do not interfere with the substrate.
Considering the potential economic losses due to hydrogen leakage, what strategies do you propose for mitigating these losses and ensuring economic sustainability of the hydrogen economy?
So what we are happy to see is that our introduction into the hydrogen industry is not adding another cost to the table. It's actually a cost eliminator, because we will be eliminating the cost of loss of hydrogen, which is estimated to $21 billion annually globally. And also, we eliminate the cost of replacing the storage vessels, being pipes or tanks, every like 10 years or so, due to the steel embrittlement or the micro cracking of other, like plastics and microfiber and carbon fibers. So, and also, when we see the big picture, we will be the enabler of increasing the green hydrogen percentage, which is what the world really needs, is to upscale the green hydrogen production. And then you need to go to places where you have green energy. And now you can do that and still have long pipelines, long transportation, long storage of hydrogen, completely lossless. And that is the three major cost drivers that are the Achilles heel today for the hydrogen industry. So I think we will be a major cost eliminator. Today, the hydrogen pipes are still being coated with high performance epoxies for anti-corrosion purposes and flow assurance. So the industry are still having these costs with coatings anyway. But we will do all of these things at the same time. It will also be a hydrogen barrier.
What are the specific challenges in preventing hydrogen embrittlement in steels?
The challenges have always been that hydrogen gas wants to connect to absolutely every material in the world. That's why you will not find hydrogen gas naturally anywhere, because it is always hooked up to anatomically something else. And once they've now spent energy creating man-made hydrogen gas, the hydrogen gas is eager to get back to its equilibrium, which is marrying something else. And that's why it will go into the steel and making it brittle. And it will also go straight through the steel and into the atmosphere. And hydrogen gas in the atmosphere is not very good. It acts as a climate gas 11 times worse than CO2, because it binds up the methanes and other gases in the atmosphere and prolong the half-life of these gases that are climate gases. So it's a very big environmental impact as well, to stop this huge loss of the hydrogen, but also economically, of course.
So, a little bit closer to your field now, how do coating techniques play a role in preventing steel corrosion, and what distinguishes hydrogen effect on steels from other atmospheric elements?
Well, our coating stops the hydrogen, which is the smallest of all molecules and atoms. And then, obviously, by nature, it will also stop all other gases, including it will stop oxygen and water and everything else that can potentially set off corrosion in the steel. And also the steel embrittlement, which is the big problem for hydrogen specific. And then when we can solve all of these things, both anti-corrosion, anti-embrittlement, anti-hydrogen losses, and still all in one coating, and you still have that flow assurance, smoothness of the surface, aligned with the specs for hydrogen pipes. That is our forte. So now we can actually we can retrofit natural gas pipes into hydrogen gas pipes instead of making new ones. And that saving is like tremendous, you can imagine. Yes.
Can you discuss the key challenge in scaling up the production of barrier coatings for industrial use and any recent advancements addressing these challenges?
Well, we are now talking to strategic partners globally, and the one thing that we need to obviously ramp up is a mass production of our coating. We also have a nano ingredient that is a very special item, which we produce in-house. This is also something we need to ramp up production to accommodate this massive market that is in front of us. So these are, and also another challenge is, of course, to be able to have sufficient amounts of applications companies to actually accommodate the spraying itself, the actual applications across the globe. So that's why we are connecting with a lot of big companies globally that has the capacity and the network to facilitate a lot of tonnage for the spraying.
How do you foresee the widespread adoption of barrier coatings impacting industries and technologies in the hydrogen economy, especially in enabling the use of low alloy steel?
Yeah, so for us, our tests have shown that our barrier coating will stick to absolutely any surface. So for us, it's not really a matter of if it's the substrate is aluminum or steel or carbon fibers or whatever. All of these substrates and materials need this coating because no material in the world will stop hydrogen leakage. The permeation will go through absolutely everything. And our coating will even stick to rock. So we know, so we're in discussions with like underground storage companies for hydrogen under pressure. So we think we can facilitate just about any of these issues and applications that will come along. And we think we will make an impact in reducing the cost of hydrogen, because if everybody goes lossless on the hydrogen and actually manage to sell all of their hydrogen that they have produced through expensive renewable energy, that will be a cost eliminator.
Regarding the diverse methods for characterizing hydrogen permeation barriers, what factors guide the choice of specific experimental setup, and how relevant are these setups to real-world applications?
Well, like mentioned, we deliberately designed the coating because that gives us the opportunity to go retrofitting on the existing pipe systems in Europe and everywhere else. And also we are now into specifics like coating internal parts of fuel cells to eliminate cross-contamination in fuel cells. Maybe that will increase the efficiency of a fuel cell and also the lifespan of a fuel cell. And also that the industry itself can go back to just using cheap black carbon steel for storage and coat it with our Triton X instead of this expensive exotic materials that are not for mass production. And of course, the retrofitting of and changing natural gas pipe networks into hydrogen gas networks. That's a big saver of money for the industry.
In enhancing the stability and durability of barrier coatings in practical hydrogen environments, are there specific areas of research or technological advancements that hold promise?
Yes. Today, we know that, let's say, a pressure storage vessel for hydrogen, they usually stop at like 700 bars, because at that rate of pressure, the hydrogen permeation is very high. And we know that with our coating, which does not even bother about the pressure at all, and then you can have the same storage vessel, and you can optimize the storage vessel's pressure specifications, which may be 1,000 bars. So then you can crank up the pressure to 1,000 bars, and you can hold a lot more energy in the same storage tank, because you have eliminated the permeation altogether. And this is a big item for, since we know that hydrogen is a very low energy per volume, but it's a high energy per kilo. So you need that pressure to carry a sufficient amount of energy. And now we can do that, because we know a lot of pipes and storage vessels, they have a higher pressure spec than what is used, because the hydrogen permeation is increasing by the increased pressure. But once you have coated with the 100% isolating barrier, that is no longer a factor. You can only now you just go for whatever the mechanical strength of the vessel, and that's your only worry. So now the industry can carry a lot more energy per unit.
What are the technical limitations, let's say, in retrofitting old pipes? Are there any limits that can stop you or prevent from retrofitting?
The limitations would be the technology to recoat long lines of pipes, and we are not experts in the applications side of this. That is, you have obviously pipe grids have maintenance programs, and they have maintenance robots and all of these things, and these are the experts on the recoating, the applications part of that, and that they might have limitations on their equipment or robots in getting access to the entire network. So that might be a limiting factor. If it's like underseas, we might be able to come up with new ways of doing it, maybe sending something we call a plug of Triton X coating through there, and it will coat itself. There are a lot of different techniques that have been used prior to this, just for maintenance purposes, and we will adopt these techniques.
You mentioned pipes and fuel cells. What are other applications in horizon?
Well, these are the two major ones. So basically, the entire value chain of the hydrogen industry needs to coat with the Triton X. Anything that are in touch, all surfaces that are in touch with the hydrogen gas needs to be coated, otherwise it will deteriorate the material and it will have leakage. We have also started a development program for our nano gaskets and nano gel to do the same, having the same ISO certification for absolutely zero permeation, and we can accommodate the industry by helping them with better gaskets and gels. And because inside pipes there's a lot of gadgets and different things that and joints that could have mechanical leaks as well, and then we need to address that as well, and not just the permeation straight through like a larger surface.
Yeah, and also the welding areas, I assume.
Yes, so there are things like that that might need to be coated after it has been assembled. So that is like technical challenges, if that it will be done by man or by robots, or how we're going to solve these things. But right now we have a development program with one of the global pipe manufacturers of the world, and we are now looking into, and the idea is for them to coat with Triton X at the factory, and obviously the welding points will be retro coated sort of on site. Yes.
Tell me about the testing. How long have you tested it, and under what pressures?
Yeah, so the hardest part with developing hydrogen barrier is obviously to be able to stop these atoms wanting to penetrate absolutely everything. So at first we tested everything at ambient pressure, but now we are into testing at 180 bars for accommodating pipes, and then this spring we will have a cooperation with several universities in the UK, where we will be testing up to 1500 bars. What we already know from our technology, that the more pressure you put on there, the better it actually works. But it's already at 100% full isolation. So, and the way this coating works is that it doesn't care about the pressure. The pressure is taken care of by the mechanical structure of the vessel.
Mm.
Because this hydrogen permeation is not so much about the pressure once you have cracked the code. It's a matter of other things on atom levels.
More on chemical side, I assume.
Yes, and of course our coating is also chemically inert and electrically inert and non-toxic, and environmentally friendly under production and also under use. So it has it all.
One more question that I overheard the other day from one professional who handles a lot of hydrogen through the pipes is that he has a water residue inside of the pipes. And it was not clear to me how water actually collects there. But is this something that you had in mind, and does this coating solve this problem?
We have tested coating under wet conditions, under rusty conditions, and even oily conditions, and it still sticks like glue. The only thing it will not stick on is oily plastic. Other than that, it will stick to all these other things. It will go through the rust layers, because you need to understand that the coating is a nano-based.
Yeah.
So it is absolutely, it just penetrates absolutely everything. And that is also why it sticks so good, because it penetrates the steel or the whatever substrate, and it just hold on to it. And it can also withstand open flame 1800 degrees without starting to run or bubble or burn or anything like that.
So basically, the water cannot penetrate this coating from outside.
No, the water cannot penetrate this coating whatsoever. Not air, no gas.
Okay. And condense and so on. So a last question is, how long does it last, let's say?
We have had age accelerated tests during the ISO 17081. And once they could see in the microscopes that there's absolutely no hydrogen atoms in the substrate, not even in the coating itself, then they cranked up the partial voltages that are in this test rig to double, because they tried to destroy the Triton X to see what it could do. They also added more aggressive electrolytes, and nothing could destroy the coating. It would still have 0, 0, 0 permeation, and nothing happened to it. So there's a big headroom for this coating before it will even break by any means. And that's whether it's pressure or temperature or chemicals or whatever. So we would say it has a lifespan of 50 years.
Yeah, that's great. So, Henning, thank you very much for being my guest today.
Yeah, thank you for being here. Sure.